In episode 73, titled Access Control Failures, IDO and AuthZ, we're focusing on access control failures as the simplest, most damaging category of web issues, getting data or actions you should not. These problems are often not flashy, which is exactly why they slip through, because teams spend time hardening authentication and input validation while assuming that once a user is logged in, the UI will keep them in their lane. Attackers do not use the UI, and they do not respect lanes. So the real question is whether the server enforces permissions consistently for every request. Access control failures often create direct privacy breaches, enable fraud, and open paths to broader compromise when sensitive actions can be triggered by the wrong users. The exam loves these topics because the correct reasoning is about boundaries and roles, not about clever payloads. The goal here is to build a clean mental model, recognize common clues, validate safely, and describe fixes and reports in a way that developers can act on quickly. Authorization can be described simply as permission checks for what a user can do and what a user can access.
Authentication answers, "Who are you?" while authorization answers, "What are you allowed to do?" And that difference matters because you can have perfect authentication and still have broken authorization.
Authorization includes role checks, such as whether a user is an admin, and it includes object checks, such as whether a user owns a specific record. It also includes function-level checks, such as whether the user is allowed to export data, refund an order, change account settings, or view administrative dashboards.
The hard part is that authorization must be enforced on every server-side request, not just on the pages the UI happens to show.
In many applications, the same back-end endpoint is used by multiple roles, and the correct behavior depends on careful checks in the back-end. When authorization is inconsistent, the app can become secure in appearance, but insecure in reality. IDOR can be explained simply as changing an object identifier reveals another user's data, because the server fails to verify that the requester is allowed to access that object. The object identifier might be an order number, an invoice ID, a user profile ID, a file reference, or any value that selects a specific record. If the identifier is predictable, such as an incrementing number, an attacker can often guess other valid identifiers and request them directly. Even when identifiers are not purely numeric, they can still be discovered through references in URLs, API responses, or user interface elements that leak the pattern. The core failure is not the identifier itself, it is the missing ownership or scope check on the server. IDOR is common because developers often assume that if the user can only see their own objects in the UI, they cannot request others, which is not true when requests are crafted manually. Once you understand IDR, you start looking for any endpoint where the client supplies an object reference. Function-level authorization failures are a related class, but instead of accessing the wrong object, the user accesses the wrong function. This can look like a normal user calling an admin endpoint directly, or invoking a privileged action such as creating users, changing roles, exporting all records, or accessing configuration interfaces. These failures often happen when access is enforced only at the page level, meaning the admin menu is hidden, but the backend endpoint is still reachable and does not validate role properly. They can also happen when developers assume a front-end route guard is sufficient, forgetting that back-end APIs must independently enforce authorization. Function-level failures are especially dangerous because they can enable direct privilege escalation inside the application, turning a standard account into a path to administrative capability. They are also often easy to exploit because they require only knowledge of the endpoint path and the ability to send a request. On the exam, if you see normal user can trigger admin action, you're almost always in function-level authorization territory. Clue patterns help you spot access control problems quickly, even before you perform any role-based comparisons. Numeric identifiers are a high-signal clue because they often imply predictability and an easy enumeration path, especially when they appear in URLs or API requests. Predictable references also include structured strings, sequential invoice codes, or file names that follow a pattern, which can still be guessable.
Inconsistent checks show up when some endpoints return a clean denial while other endpoints return data for the same kind of object, suggesting that authorization logic is not centralized or consistently applied.
Another clue is that the application uses the same endpoint for multiple roles, but relies on the client to filter results, which is a common anti-pattern. You also watch for endpoints that accept object identifiers as direct parameters without additional context, because that often signals a missing ownership check. These clues do not prove a vulnerability, but they tell you where safe validation is likely to pay off. The impact of access control failures is often immediate and business relevant, which is why they rank high in real prioritization. Privacy breaches are a common outcome, especially when one user can view another user's orders, profiles, or documents. Fraud becomes possible when actions like refunds, transfers, or account changes can be executed by the wrong role or against the wrong object. Data tampering is another outcome, when unauthorized users can modify or delete records they should not be able to touch. Account takeover paths can also emerge indirectly, such as when an attacker can access password reset tokens, API keys, or sensitive account settings for other users through IDOR.
The important point is that access control failures often require no sophisticated payload and no exploitation of complex bugs. They require only the ability to make a request.
That simplicity increases likelihood, which is why these findings tend to be urgent when confirmed. When you can tie impact to real business outcomes, the finding becomes harder to dismiss.
Safe validation is about testing with two roles and minimal object changes, because you want proof without causing harm. Two roles can mean a standard user and a privileged user, or two different standard users, depending on the application's role model and what you have authorization to test. Minimal object changes means you adjust only the identifier or the requested function just enough to test the boundary, and you stop as soon as you confirm that the server returns data or accepts actions it should deny.
You avoid bulk enumeration, automated scraping, or pulling large datasets because those actions increase harm and are not necessary to prove the control gap. You also choose low-sensitivity objects where possible, such as test orders or non-production records, while still demonstrating the permission failure. The goal is to show that the server is missing an enforcement check, not to demonstrate how much data you could harvest if you behaved badly. Safe validation makes your findings credible and keeps the engagement professional. Now, consider a scenario where changing an order number reveals another order, because this is one of the clearest IDOR patterns.
Imagine a user can view their order by requesting an order endpoint with an order number, and when you change that number to a different valid value, the application returns details for a different customer's order.
The clue is that the server accepted the object reference and returned the object without verifying ownership or authorization scope. This is IDOR because the vulnerability is the direct object reference, and the exploit is simply changing the identifier. The safe validation approach is to confirm the behavior with a minimal number of tests and to capture only the minimum evidence needed, such as the fact that the order belongs to a different user and that the response includes unauthorized fields. You avoid capturing full order contents or exporting multiple orders because proving one unauthorized access is sufficient to establish the control failure. This scenario also naturally supports remediation guidance because the fix is clear. Enforce server-side ownership checks for every object access request. A second scenario involves a hidden admin endpoint accepting normal user requests, which illustrates function-level authorization failure. Imagine you discover an endpoint path that performs an administrative action, such as changing user roles, issuing refunds, or exporting data, And you find that a normal user can call it successfully because the backend does not enforce role restrictions.
The clue is that the UI might hide the admin function, but the server still executes it for an unprivileged user, proving that authorization is not enforced at the correct layer.
Safe validation here means issuing the smallest request that demonstrates acceptance without causing irreversible change, such as using a non-destructive admin action if available, or testing with a dry run parameter when such a mechanism exists.
If only state-changing actions exist, you coordinate and use test data or controlled accounts so you do not impact real users. The outcome is strong evidence of a privilege boundary failure, and it typically warrants high priority because it enables direct escalation inside the application.
This scenario reinforces that hiding routes is not security. Server-side checks are required. A common pitfall is assuming you are dealing with authentication problems when the real issue is authorization, because both can manifest as access you shouldn't have. Authentication failures are about bypassing login or identity verification, while authorization failures are about what a logged-in user can do. If you misclassify an authorization issue as an authentication issue, you may recommend wrong fixes, such as stronger login controls, while leaving the broken permission checks intact.
Another pitfall is overemphasizing technical complexity, looking for injection or cryptographic flaws, while ignoring simple role and object tests that would reveal access control gaps quickly.
It is also easy to mistake an inconsistent user interface for a security boundary, which leads to under-testing of direct endpoint access. The professional approach is to be explicit about layers, confirm you are authenticated, then test authorization boundaries directly using controlled requests. When you do that, the correct classification becomes much clearer.
Remediation concepts revolve around enforcing server-side checks, denying by default, and applying least privilege consistently. Server-side checks mean the backend must verify both role permissions and object ownership for every request, regardless of what the client UI shows. Deny by default means that if the application cannot confirm that access is allowed, it should reject the request rather than guessing or returning partial data. Least privilege means roles and permissions should grant only what is needed, and sensitive actions should require explicit privileges rather than being available broadly. Centralizing authorization logic helps reduce inconsistent checks because developers can reuse a standard policy evaluation mechanism rather than re-implementing checks in each endpoint. Strong object access controls include verifying that the object belongs to the user or that the user's role includes explicit access to that object's scope.
These concepts map cleanly to engineering work and are typically more effective than adding superficial UI restrictions.
Reporting language should show the unauthorized access path and the affected objects clearly, because defenders need to know what to fix and how to verify the fix. You describe the affected endpoint or function, the required authentication state, and the role or user context under which the unauthorized access occurred.
You describe what object or action was accessed, such as another user's order or an admin-only function, and you describe impact in practical terms, such as privacy exposure or unauthorized administrative control. You keep evidence minimal and responsible, showing that the returned record belonged to another user or that the action was accepted without privilege, without including sensitive data beyond what is necessary to prove the point.
You recommend specific controls such as ownership checks, role checks, deny by default enforcement, and centralized authorization logic.
Clear reporting also notes scope constraints and safe validation choices, reinforcing that the finding was confirmed without harming users. This makes the finding both credible and actionable. To keep the core logic clear, use this memory anchor. Identity proves who, authorization proves allowed. Identity is authentication, which establishes who the user is, while authorization determines what that user is permitted to access and do. When you hold that distinction, you stop blaming login systems for what is really a permission boundary problem.
It also helps you structure tests. First, confirm identity state, then challenge the allowed actions and object boundaries. The anchor guides remediation thinking too, because fixing authorization requires server-side checks and policy design, not just stronger passwords.
On the exam, this distinction often separates the correct answer from a tempting wrong one.
If you can say the anchor sentence quickly, you will classify scenarios more reliably. To conclude episode 73, titled Access Control Failures, IDOR and AuthZ, remember that these issues are about missing permission enforcement, and they often produce high-impact outcomes with low attacker effort. IDOR is about object-level authorization, where changing an identifier reveals data that should be out of scope, while function-level authorization failures are about executing actions reserved for higher roles. Safe validation uses minimal role comparisons and minimal object changes, and remediation relies on server-side checks, deny-by-default behavior, and least privilege policy design. Now, classify one example as IDOR or AuthZ. If changing an order number returns another customer's order details, that is IDOR, because the object reference is being accepted without an ownership check.
If a normal user can call an admin endpoint that performs privileged actions, that is a function-level authorization failure because the server is not enforcing role-based permissions.
When you can make those classifications cleanly, you have the access control model the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.